Hello, multivariable calculus students. This is Mr. Johnson, and this is section 11.4. We're going to talk about tangent planes and linear approximations. So let's start with our formula. You can see in our definition here that if you have an equation of a tangent plane to a surface z, which we could call f of xy at the point x sub 0, y sub 0, z sub 0, we have the following formula for the plane. You're going to see a lot of similarities between this formula and the plane that we have discussed in the past. And let me just point out a couple quick things. So number one, we have our generic form of an equation for a plane that we discussed in the past sections. And ABC is going to be the vector that is perpendicular to the plane. So remember, we call that the normal vector, and that's how we've written planes up to this point with some initial points. So you can see that it's really similar, the comparison between these two formulas. However, you notice that you have the z minus z sub 0. That doesn't have a multiplier in front of it. In this other formula, we have c. But now, instead of a and b and c, we have these partial derivatives that show up. And so I just want to quickly explain where those come from, or at least try to demonstrate where they come from. So let's take a look over here at our diagram in the notes. We have a surface, and this particular surface has two tangent planes. So we have t sub 1 and we have t sub 2. T sub 1 is the tangent plane that lies on the surface at a point such that y is held as a constant. So in other words, this tangent line, is parallel to the xz plane. And then the second tangent line is when x is held constant, and that's going to be parallel to the yz plane. So let's start with the t sub 1, the first tangent line that we see here. So we're going to let y be constant, which means that if we're going to go through the point that we've been given in the definition of x sub 0, y sub 0, z sub 0, that means that y is always y sub 0. And so let's go back over here to our generic equation and just think about what this means for us, okay? So what we have is our original equation, and I'm going to rearrange this slightly. So I'm going to take and move a few items over to the right side. So I have negative a x minus x sub 0 minus b times y sub y minus y sub 0, and then I'm going to divide by c because I want to make sure the z is alone on the left side, and this just mimics the equation that we're dealing with in the definition we're given in our notes. And I just want to point out the similarity between the two. So if we're looking, for example, on the tangent line t sub 1, like I mentioned, y is going to be a constant and y is equal to y sub 0, because if you look at your diagram in the notes, that tangent line goes through the point, and if y is a constant at that point, it's going to be y sub 0. Now what this means is that if we look at our generic equation that we have here in blue, if y is equal to y sub 0, then all of this cancels. And so what we're left with in this case is z minus z sub 0, and then negative a over c multiplied by x minus x sub 0. And again, the y values would cancel because y is constant, y is equal to y sub 0, and so that whole second expression would cancel. Now what this means is that we have this line in space. However, we can sort of think of it as a plane, as a line on a plane, because we've eliminated this third variable y. We're only dealing with x's and z's. And so if you can sort of picture this in space, the y does not impact the equation. This is simply just a tangent line, similar to the ones that we've dealt with in the past, where it's just made up of two different variables, x and z in this case. And of course, this is going to be your slope of that particular tangent line. Again, this is a connection to single variable calculus. Now, the challenge for us is, okay, what is the slope of that particular tangent line? Well, remember, that's where we have partial derivatives. So in our case, we have a function z, which is made up of x and y. However, we've taken y and made it a constant. So think about what is the derivative of z when y is a constant. That derivative is going to be the partial derivative of z with respect to x. So we have a sort of a substitute here for this unknown variable that we had in the past. So this unknown negative a over c is now really just that partial derivative of z with respect to x. And that's where in our formula you can see that f sub x derivative show up. That's where that partial derivative comes from. And I'll make the connection here in just a minute. Let's talk quickly before we do that about the second tangent line. So on your diagram in your notes, you have the second tangent line, which is t sub 2, and that's when x is equal to x sub 0. I'll speed through this one a little bit faster so as not to bore you too much. And we have the x values cancel. So again, I'm back here in the blue, and the x values are going to cancel because x is equal to x sub naught in this case, because that tangent line is parallel to the yz plane. And so you're left with this equation of a line. Again, we're going to revert back to this idea that now we're sort of in this two variable space because x is relatively eliminated in a sense. And so therefore we're looking at what is the slope of this tangent line with respect to y only. And that's going to be the partial derivative of z with respect to y. And that is where we're going to get our generic form. Now I'm going to make one note here. Remember that that in our equation in the notes, we often label z as f of xy. And so we could label this as the derivative of f with respect to x, that partial derivative, or similarly the derivative of f with respect to y. You could call this all sorts of things. You could do that partial derivative notation. Okay, so keep in mind that you can notate this many different ways. But let's just go back to the notes really quick. Notice where we come up with this idea that if we have the tangent line where y is held constant, well, all of a sudden there's your tangent line of two variables. If x is held constant, that's eliminated, and that's going to be your tangent line where x is the constant and the z and y are what makes up the tangent line itself. So we put it all together, and this is going to be the tangent plane equation, and it's really easy to write simply because we're taking two really quick partial derivatives and using those as the changes along the x and the changes along the y's. Okay, so that's the background. That took a lot longer than any one of these problems, to be honest with you. So let's try example 1. It's pretty fast. The tangent plane to the paraboloid z equals 2x squared plus y squared at the point 1, 1, 3. So we're going to calculate the derivative with respect to x first. So the partial derivative, we get 4x, and the partial derivative with respect to y, and we get 2y. And so we're just going to simply calculate each of these at the given point. So we get 4, and for the second one, we get 2. And then we're going to substitute this in for our formula. So our formula, let's see, this is our first one, so I'll slow down here. So we have z minus z sub 0, which is equal to the partial of z with respect to x times x minus x sub naught, plus the partial of z with respect to y times y minus y sub naught. So where does all of this come from? Well, our point is going to be x sub 0, y sub 0, and z sub 0. So we get all of the information that we need there. And then, of course, we need our partial derivatives, which we've calculated to be 4 and 2 in this particular moment. So here we go. We got z minus 3 equal to 4 times x minus 1 and 2 times y minus 1. And there you go. That's kind of all there is to it in terms of the plane itself. All right, now below this, there's a visual that I think is helpful. I'll talk more about this visual when I talk about linear approximation in a moment. The idea here, it really is similar to the single variable calculus interpretation. It's identical, actually. It's just in space now. So if you have this surface that's curved, more or less, you have a tangent plane, that touches only at one point, just like a tangent line would touch a curve at one point. And if you zoom in and zoom in more and more to that point, so you get closer and closer to that point you're looking at, the surface and the tangent plane become more and more similar. That's the local linearization aspect of what we're doing with derivatives and tangent lines or tangent planes. You can see that if you were to take a look below at the contours of this, the closer we get to the point of where the tangent plane touches the surface, the more the contours are going to be linear. Okay, and that's the whole idea of linear approximation or linearization of some sort of model. Okay, all right, let's move on and talk about example number 2. All right, example number 2 is really the same concept. In fact, example 2 and 3, I'm just showing you 2 more times, 2 different examples, but it's the same concept. Okay, so if you feel like you got it and you want to try it on your own and then check with the video, that's completely fine. We're going to take the derivative with respect to x. It's going to be 6 times the quantity x minus 1. Oops, sorry. And then we're going to do the derivative with respect to y. And that's going to be 4 times y plus 3. And we'll calculate both of them at our point, 2, negative 2, and 12. So we get 6 for that one, and 2, negative 2, and 12, and we get 4 for this one. And then all there is left to do here is to substitute our values in. So remember the z value to the point is 12, so we have z minus 12 equal to the partial with respect to x, which is 6 times x minus 2, and the partial with respect to y, which is 4 times y minus negative 2, so y plus 2, and that's it. You can rearrange that if you need to, or simplify, distribute, that kind of thing. That's okay. All right, let's try example 3. So another tangent plane to this surface, x is 3 and y is 1. So again, we find our partial derivatives. This one might be a little more challenging in terms of the partial derivatives just because it's the natural log function, which can get a little messy. Remember, for the derivative of y, we have to use the chain rule because the derivative of the inside is not, or no longer 1. So we have the partial with respect to x, which is 3, 1. I don't know what the z value is. We'll figure that out in a second. So we have, let's see, 1 over 3 minus 2, so that's going to be 1. And then we'll do the second one. So we know that's 1 over 3 minus 2. And then we multiply by negative 2, so we're going to get negative 2 for that one. I haven't calculated z yet, so let's go ahead and take z, and we're just going to substitute in x and y to that. So we have the natural log of 3 minus 2, and that happens to be 0. Okay, so our answer would be z minus 0, of course, equal to the derivative with respect to x is 1 times x minus 3, and then the derivative with respect to y is negative 2 times y minus 1, and there's your tangent plane. Okay, so that's our first concept in this section, is can we calculate a tangent plane to a surface in the Cartesian form? We'll talk about the parametric form at the end of the section. What this leads us to, and what I alluded to in the previous page, is that the idea behind any kind of tangent analysis of a function really boils down to an approximation of sorts. Remember, at the point of tangency, it is perfect. The tangent plane touches the surface, the values are identical, but elsewhere, it often doesn't touch the surface again. So in other words, you have this situation. I'm going to zoom down here to the diagram at the bottom of the page. So you have this spot where the tangent plane touches the surface and they're equal. However, if you move away from that point in any kind of direction, the surface would pull away from the plane, which is going to be constant. And so the plane and the surface are similar, but they're not exact. Obviously, the further you go from the point, the idea often is that they're further and further apart. Now, obviously, you could have some sort of surface that would come back and meet the plane, for example. But the idea is that if we were able to put together a tangent plane equation and we were able to maybe move away from this point slightly and find a point on the plane, then we could claim that it would be similar to the point on the surface. So maybe we would come up with some sort of approximation using the plane rather than using the surface, because maybe we don't have enough information about the surface. Obviously, we know exactly what happens at this point, so that's not very helpful, but if it's just slightly off that point, we're able to find that similar value on the plane. Okay, so that's the idea of a linear approximation or a linearization. Again, you can see in the notes, it talks about the visuals from example 1. I mentioned those visuals and the contours and how they become this linear, almost this linear relationship. But here's your equation, and I want to make sure to highlight this because I think it's important to understand that a linear approximation is really just the same equation of a tangent plane, just written differently. So, for example, if we kind of go back, oops, sorry, if we go back to the equation we had on page 1. Okay, so this is the tangent plane. Now, what we're saying is that we want to approximate the value of the function. So let's say the function is z equal to f of x, y. If we want to approximate that, we could simply move the z sub naught over. So we would have z equals z sub naught plus f of x times x minus 0 and f of y. And by the way, the notes outline this. I'm just kind of rewriting it again. So just so you're aware of what's going on here. I'm kind of just repeating what the notes are stating. So if we know that z is equal to f of x, y, well then we can simply just take the z right here and we could just write it as f of x, y. And we're going to just rename this to be L of xy. Now, why is that? Well, basically, we're just stating that there's some sort of linear approximation going on here, which is going to be equal to z sub naught, which is the very first value. I'll just leave it for now. And here's the rest of it. And so all we're doing here is just rewriting the name of it. We're not really changing anything. We're just rewriting the name, and we're calling it a linear approximation. And what we're saying essentially is that the function value is similar to the y value or the z value of the tangent plane. That's all we're claiming, okay? But so really we're just doing the same plane. We're just changing the name of the z to be L of xy to represent a linear approximation. So here we go. Let's try one of these. Just again, this is so similar to single variable calculus that you've seen in the past. We're just making a connection to the plane itself. So we're going to figure out the plane by taking the derivative with respect to x first. So we get 2x minus y. Let's go ahead and evaluate that at 3, 2. So that's going to give us 4 and f of y, which is, let's see, negative x plus y. And we'll go ahead and evaluate that as well. That's going to be negative 1. I do need the function value at 3, 2. So let's go ahead and substitute that in. Let's see, this is going to be 9 minus 6 plus 2 plus 3. So let's see, that's going to give us 8. And that's going to be our function value at this point. So our linearization, or our plane, is going to be z minus 8 equal to 4 times x minus 3 minus 1 times y minus 2. Now all I'm going to do is I'm just going to rewrite it because it's asking specifically for a linearization of a function. So I'm going to let z be L of xy, and I'm going to move the 8 over. Those are all based on the directions above. And there we go. That would be a formal linear approximation. Okay, let's move on to the next page and try example 5. All right, example 5. Same thing here, except we're going to use the linear approximation. So let's do the linear approximation first. We have f sub x, so we have e to the xy. Be careful here because this is the product rule, okay, and the chain rule. So when I'll back up here. So when we're taking the derivative of this, x times e to the xy, derivative of x is 1. So I have just e to the xy plus x times the derivative of e to the xy, which by the chain rule would be a multiplication of y. So this is the product rule with the chain rule. We're going to evaluate this at 1, 0, which happens to give us, let's see, if y is 0, we're going to get 1. And then we have f sub y, which is going to be, this is just the chain rule here. That's going to be x squared e to the xy. and we'll evaluate that at 1, 0, and that happens to be 1 as well. We also need the function value, so the function value at 1, 0 is, believe it or not, 1. Look at that, everything is 1. Okay, so our linear approximation will be, let's see, the function value of 1 plus 1 times x minus 1 plus 1 times y minus 0. And I think for ease, let's see, that's just going to simplify to x plus y. So that's your linear approximation. And we're now going to use that to approximate f of 1.1 and then negative 0.1. So we're going to approximate this function value. Keep in mind the idea is that if I was to take this and substitute it in, I wouldn't be able to do that in my head without a calculator. However, with the tangent plane, I'm able to calculate it pretty quickly without using any kind of calculator. So that's the goal here. All right, let's back up. So we're going to take and just simply substitute this in. I'll label this as the approximate right now. So we have f of 1.1, negative 0.1 is approximately L of 1.1. And I'm using my equation for L, which is just 1.1 minus 0.1, believe it or not. It's 1. Everything is 1 in this problem. Okay, let's just, for, I guess, discovery's sake, what is the actual? Well, the actual is f of 1.1, which is, let's see, 1.1 e 1.1 times, all right, I'll type this in. Okay, so I typed it into my calculator and I got 0.9854. So again, we're pretty close to the actual here, but the actual, obviously we need the calculator versus the approximate. We can just take the plane, and that's one of the purposes of that linear approximation model. Okay, that does it for the first part of this. Next, I'll talk about differentials, and then I'll talk about the parametric form. Thank you.